Okay, so today we're looking at the second part of our exploration of significant figures. All right, and so today we're going to be focusing more on why we have to worry about significant figures and why the various rules that we've learned come into effect. So we're going to start off with a quick little discussion of rounding. All right, so we've already been here. If you've been in class over the last couple days, or maybe seen this in prior classes, but a big part of dealing with significant figures is in knowing how to round. Okay, so we're going to take a series of numbers and we're going to round them to various different place values. All right, so the number we're going to start with is this: 3,259.56. We'll go 7. All right, and we'll give that a unit of grams. Okay, so we've got your different place values here. And we can label all those if we like. All right, spin this here. So you've got your ones, your tens, your hundreds, the thousands. Okay, here your tenths, hundredths, and your thousandths. Okay, so thousands, hundreds, tens, ones, tenths, hundredths, thousandths. Okay, so all the ones smaller than the decimal place end in that th sound. Okay, so let's take this number and we're going to try and round this to the nearest. Let's just go ahead and do all of these. We're going to round to the nearest 1,000. Okay, so what that means is we're taking this number, we're counting by thousands: 0, 1,000, 2,000, 3,000, 4,000, 5,000, and so on. And we're seeing which one of those thousands this one's closest to. So I think we can all see, hey, it's pretty close to 3,000. It's only 200 more than 3,000. So it's going to round to 3,000. Okay, and that would be in grams. Now, I'd like you to notice this one thing. For those of you who've already seen the other video, we have seen that this number, 3,000, only has one significant figure. Okay. Now, when we round to a certain place, we lose all the information of places that are smaller than it. Okay, so here we round to the thousands. We lost the information about the hundreds and the tens and the ones and the tenths and the hundreds and the thousands. We lost that. We were rounding to a really big place value, so all of the little stuff doesn't really matter. Keep in mind, it's only because we know our original number, that we end up rounding to this 3,000. If we just saw the number 3,000, something that was rounded to the nearest thousand, that could be a number anywhere from 2,500 rounding up all the way up to 3,449. Well, 99, excuse me. And if it's rounding down. Okay, if we just see the number 3,000 and we know that it's to the nearest thousand, here is your one significant figure. All right, it could be anywhere in this range, 2,500 up to 3,499. Okay, that's a range of almost 1,000, just under 1,000 on either side. Okay, well, 500 on either side, total range of 1,000. The fact that we're rounding to such a large place value means we lose a lot of certainty in the rest of our stuff. So if we're not even sure if this is between 2,500 and 3,499, speculating as to what is in this hundreds place doesn't really matter, because we've got 1,000 places where we could be anyway. So let's see where this is, rounding to the nearest 100, and to the nearest 100, right here? Well, we see this 59. The 5 in the tens place is going to actually make that 100 round up. So rounding to the nearest 100 would be 3,300 grams, and this one would have 2 significant figures. Okay. Now rounding to the nearest 100, we're a little bit smaller of a range. If we round to the nearest 100, we know we're in the range 3,250 all the way up to 3,349. Okay. You see similar, it's a range of about 100. If we round to the nearest 10, we would round to 32, that's going to stay the same. And then we got to figure out 59. Well, 59 is going to round to 60. And here we have 3 sig figs, and so on. And this range, it could be anywhere from 3,255 on up to 3,264. Okay, so our ranges are progressively shrinking as we allow ourselves to round to a smaller and smaller interval. Okay, so kind of a discussion of where are we and why does this matter. Okay, significant figures tell us how much uncertainty there is in our measurement. All right, so this number rounded to 3 significant figures. You'll notice that we rounded to 3 significant figures, it's the 3 largest. Rounded to 2 significant figures, it's the 2 largest. 1 significant figure, it's the 1 largest. When we round to increasing numbers of significant figures, our uncertainty decreases. Here we're only uncertain by 9 units. Here we're uncertain by 999 units. Okay? So let's take a look at a couple of the individual rules and show why they actually matter. Okay? So we looked at 2 rules, okay, in specific at the beginning. Well, we looked at 5 of them in the other video. First one's pretty straightforward. Anything that's non-zero is going to be significant. Well, why? Because all of those we know have been measured. The second one is where we start looking a little bit more in depth. Anything that's sandwiched between 2 significant digits is going to be significant, and the reason why, that significant digit at the end has been estimated, which means that this 0 has been measured. Okay, the last significant digit in any measurement has been the one that's been estimated. So here this 2 has been estimated, which means this 0, and that 3 have all been measured. What this 3002 is saying is that we are somewhere between 2,990, 3,000, 3,010. We're counting by tens. We've estimated that it's about 2 units past 3,000. That's what this number is telling us, and that's why these zeros here are important, because for these guys to be estimated, we have to have measured these zeros, and anything that we measure is going to be significant. Taking a look at the next rule, zeros that are placeholders are not significant. Now, what does this mean? These placeholders at the end of whole numbers, they basically shift what we are measuring, shift the size of what we're measuring. Okay, in here we've measured 1/1000, and we've estimated 200s. Here we've measured 1/100 and estimated 2 tens. Here we've measured 1/10,000 and we've estimated 2 1,000s. You'll see that the things that the measurement that we made didn't change. 1 larger unit, and then we've estimated 2 of the smaller. All these zeros do is show us how big that measurement is. It doesn't actually tell us what we've measured. Okay? And that's the kind of the big sticking point here, is that we measure using the tools that we have, and that tool doesn't matter. The measurements we get out of it are significant based on our estimations of that tool. So here, these zeros just show us that we're using a much larger tool than here. And this one measuring 100s, estimating 10s, is a much smaller tool than this one, which is measuring 10,000s and estimating thousands. In the same view, it's the idea here, where we're measuring one 0.01 unit, and we've estimated 2 0.001. Here we've measured 1 0.0001, and we've estimated 2 0.00001. Okay? Here we've measured 1 0.001, and we've estimated 2 times 0.0001. Okay, again, all of these zeros only go to show what size our tool was. Doesn't tell us anything about the precision of the tool, doesn't tell us anything about the actual measurement that we weighed. We've made one measurement at a bigger unit, and we've estimated 2 of the smaller. These placeholder zeros only show us the size of the tool that we're using, not anything about the actual measurement. This one may be the hardest rule to get. All right, zeros at the end of a decimal are significant. Okay, and the reason being is it tells us more about the tool that we used. And again, and this is a kind of a point that we're going to belabor a lot. What we do in science is try to share our results so that we can get other people to confirm them or to refute them. Science is collaborative that way. So by including this kind of information, it shows what kind of tools we were using, and it allows us to be more explicit in terms of what we were actually doing. So when we see 13.0 centimeters, here's what it means. It means we've measured 12, 13, 14, we've measured the 13 centimeters, and we estimate that it stops right there. That's that 0.0, that estimated digit right there. If we were to just write 13, it would basically be like we're counting by tens, 0, 10, 20 centimeters, and we've estimated it's 3 past 10. Similarly, if we're looking at graduated cylinders, 2 milliliters means that we are somewhere in between 0 and 10 to the point where we think it's right around 2 units up. 2.000 milliliters means that we have measured 1.99 milliliters, 2.00 milliliters, 2.01 milliliters. The meniscus is coming down right at that 2.00 milliliter mark. It's showing that we've got a much more precise instrument than 2 milliliters would show. Okay. So again, this is all about showing off the equipment that you're using, all right? The types of equipment, the types of tools that you have, and making sure that we are being as precise as we need. We already went through the exact numbers, all right? Anything that's defined, like a dozen or a score, that's an exact number, and it's not going to have, or it's going to rather have infinite numbers of significant figures. I can count these dots. I'm not estimating that there are 10 and then maybe one more. I'm saying there are 11 of them. I can count them, and that is going to be an exact number. So if we wanted to visualize this, it would basically be 11.000000000 on out into infinity. All right, however many zeros we needed to have. So, all things considered, let's take a look and see why significant figures matter. I'll give you one example here. Let's say, and this is going to be a strange example, so bear with me, all right? But just for argument's sake, let's say you are measuring your lawn because you want to, or rather your backyard, because you want to build a fence. Okay, so here's your backyard, green grass. Now let's say you've only got one tape measure to do this, okay? And you measure this this thing here, and you want to be as precise as possible because you don't want to buy too much fencing. Let's say you measure this thing, it's a meter tape measure, and so you manage to measure this at 43.26 meters long. Okay, 46.2 meters long. Well, for whatever reason, you managed to break your tape measure. Okay. So when you're going to measure this side, you don't have your tape measure, nobody's able to drive you to the store, you don't have any money, whatever, you don't have another tape measure. And you just estimate this, and you say, that looks like it's about 30 meters. Okay? Well, I think I misspoke earlier. I said we're buying a fence. Now let's think about we're buying a fertilizer. We've got to fertilize our entire lawn. We need to know the area here. All right, we need to know the area. Well, remember what we're saying, this is about 30 meters. That means that this could be anywhere, in our estimation, anywhere from 25 up to 34 meters. Okay? We're not really sure. Okay? It is somewhere in that range. So if I want to find the area, let's see what we do. We would multiply 30 meters times 43.26 meters. Okay, and let's see what that turns out to be. Got to run the calculator here. And it turns out that this would come out to be 1,297.8 square meters. Now, that's the calculator answer. But let's consider why it doesn't really make sense to give this entire answer here. We don't know if this is on the 25 side or the 34 side, or whether it's actually right there at 30 meters. We don't know. So let's just, for sake of argument, let's do if it was 25 meters. So we got 25 times 43.26, and that gives us 1,081.5 square meters. Let's see what happens if it's 34 meters. And see what the area is then. 34 times 43.26 meters. And that gives you 1470.84 square meters. So check that out. The only thing they actually agree on is that it's going to be somewhere between 1,000 and 1,500. It's not really all that good. All right, we can't be pretending that we know what the 100 or what the 10 or the 1, and especially not the 10th here, is going to be. If we're not even sure, we've got a 400 square meter difference between these two. Okay, we've got a 400 meter square difference between these two answers, between these two estimations. So we absolutely can't pretend that we know this information this well. That's why when we do math with a multiplication and division specifically with these problems, we look at numbers of sig figs. 4 sig figs here, 30 meters, only 1. The only thing we really truly know is that this is going to be at least 1,000 and less than 2,000 square meters. So I would take this number, round it to my largest significant figure, and say that it's going to be somewhere around 1,000 square meters. Okay. The difference between, or the range in possible answers is so great that we can't pretend to have the information on that 100s or the 10s place at all. Okay. In a similar vein, this is just an interesting question for you. If you ever want to really amaze your friends. All right, you're at a stadium. Let's say you're at a football game. The announcer says, looks like there's about 60,000 people in the stands. And as the announcer is saying that, you see one person gets up to leave. How many people do you have left in the stadium? The answer is still 60,000. Because if you're looking out at the crowd, you're estimating the 10,000s place. One person, when you're estimating 10,000, makes absolutely zero difference. Alright, so just a little fun fact, fun with sig figs, you can raise all your friends. I hope this helped. If not, please come on in, shoot a message over, and let's try and get this all put together.